So for this example, we have here the limit of the function x squared minus 1 all over x plus 1 as x approaches to negative 1. So in finding the limit of the function, first we have to factor out this expression, which is the x squared minus 1, because it is factorable. So factor out that one we have here. So after factoring x squared minus 1, we have here x plus the quantity of x plus 1 multiplied to quantity of x. And we have here the quantity of x minus 1 multiplied to the quantity of x plus 1 as the factor of x squared minus 1. And we're going to copy the denominator, which is the x plus 1. So we have here the limit of the function x minus 1 quantity of x minus 1 multiplied to the quantity of x plus 1 all over x plus 1. So this one for in this step is we're going to cancel out x plus 1 on the numerator and the denominator, and now we only have the limit of the function x minus 1 as x approaches to negative 1. So we're going to apply the limit. So in applying the limit, we're just going to substitute negative 1 as the value of x. So negative 1 minus 1 is equal to negative 2. So therefore, for this example, L'Hopital's rule does not apply because the limit is not indeterminate, because we have here the value of negative 2. It can be simplified and evaluated directly. So in using L'Hopital's rule, we have to remember that the first step is to evaluate the limit or evaluate the limit, and we have already evaluated the limit in this example, and the result was not indeterminate because we have here the value of negative 2. Therefore, we doesn't need to continue in applying L'Hopital's rule, which is finding the derivative of the function, because we already have the limit, or the limit is equal to negative 2. So that's it for this example. So now let's solve another example. So we have here the limit of x minus sine x all over x cubed as x approaches to 0. So now let's find the limit of this function. So before we opt to use the L'Hopital's rule, the first step is to evaluate the limit first, to determine if the limit is indeterminate. So if this example have a value after evaluating the limit, we doesn't need to use L'Hopital's rule anymore. So let's find out. So now we're going to apply the limit. So for this example, we're just going to substitute 0 as the value of x, so in this function. So that's it. So after substitution, we have here 0 over 0, which is indeterminate. So we will apply L'Hopital's rule, because that is the condition that we need to fulfill in applying L'Hopital's rule. So applying L'Hopital's rule means that we're going to find the first derivative of this function. So now the first derivative of this function. So the first derivative of the numerator, which is x minus sine x is 1 minus cosine x. And the derivative of the denominator, which is x cubed, is equal to 3x squared. So now we have here this function. So now let's apply the limit. So in applying the limit, once again, we're going to substitute 0 as the value of the value of x. So we have here 1 minus cosine 0 all over 3 multiplied to 0 squared. So cosine 0 is equal to 1. So we have here 1 minus 1 over 0, which is again indeterminate. So we need to apply L'Hopital's rule again. And applying L'Hopital's rule again, which means that we're going to find the derivative of this function, or the second derivative of our original function. So now the derivative of 1 minus cosine x is equal to sine x, and the derivative of 3x squared is equal to 6x. So now that is our function. So now we have the function the limit of sine x all over 6x as x approaches to 0. So now let's find out if we can now have a value of our limit after evaluating the limit. So apply the limit, substitute 0 as value of x. So we have here sine 0 all over 6 multiplied to 0. And once again, it is still indeterminate. So we're going to apply L'Hopital's rule again. So in applying the L'Hopital's rule again, we need to find the derivative of this function. So the derivative of sine x is cosine x, and the derivative of 6x is equal to 6. So we have here limit of cosine x over 6 as x approaches to 0. So now let's find out and apply the limit. So we have here cosine 0 over 6. So cosine 0 is equal to 1, and we just copy the denominator, which is 6. So we have here 1 over 6, or 1/6, and that is our answer. So now we have already the limit of the original function is equal to 1 over 6. So we have here our example, finding the limit of the function x raised to 1 all over x as x approaches infinity. So for this problem, this is quite tricky because it takes on the form, or the other indeterminate form of infinity raised to 0. So in order to solve this problem, is we're going to use logarithms to simplify. So first is we're going to let y equals to the function, which is x raised to 1 over x. And now we're going to find the natural logarithm of both sides. We have here ln y is equal to ln quantity of x raised to 1 over x. So based on the logarithm property, ln a raised to b is equal to b multiplied to ln of a. So for this example, which that means that ln y is equal to 1 over x multiplied to ln x, because 1 over x is our exponent. And we can simplify that into ln x over x. So now, in order to to know if we can possibly apply the L'Hopital's rule for this specific example, the first condition is to know if the function is indeterminate, so evaluate the limit. So we have here the limit of ln y as x approaches infinity, and which is equal to the limit of ln x all over x as x approaches to infinity, because that is the value of our y. So substitute infinity on the x as the x value. So we have here infinity over infinity, which is indeterminate. Since the limit is indeterminate, we can apply L'Hopital's rule. So now let's apply L'Hopital's rule. So in applying the L'Hopital's rule is we're going to find the first derivative of the function. So the first derivative of the function, which is so the first derivative of the function is equal to the limit of 1 over x as x approaches to infinity equals to 0. So because we derived the derivative of ln x is 1 over x, and the derivative so the derivative of ln x over x is 1 over x, because the numerator, the derivative of ln x is 1 over x, and the derivative of x is 1. So now we're going to substitute infinity, and the result is equal to 0. So in solving problems like this one, so we have already found the value or the limit of our y. So in solving this type of problem, we have to remember that the limit of y as x approaches to infinity is equal to the value of the y, which is the function. Our function for this example is x raised to 1 over x, as the limit of x raised to 1 over x as x approaches to infinity is equal to e raised to the limit of the function ln y as x approaches to infinity. So based on our solution, we have already found the limit of ln y, and the limit is equal to, that's right, equal to 0. And e raised to 0 is equal to 1. Therefore, for this example, the limit of the function x raised to 1 over x as x approaches to infinity is equal to 1. So this example is quite tricky because it involves using logarithms, and we need to find the we need to undo the logarithms and use to exponentiate both sides. So for this example, we're going to find the integral of 3 over x raised to 5 dx from 0 to 1. So for this example, it takes on the form of this one, which is the limit of f of x dx, or the limit of the integral of f of x dx from t to b as t approaches to a to the right. So this example is an improper integral, which takes on this form. So now we have here the limit of the integral of 3 over x raised to 5 dx from t to 1 as t approaches to 0 to the right. So the first step in solving this problem is we're going to find the antiderivative of um, this function. So we have here the integral of 3 over x raised to 5 dx, and it can be rewritten as 3x raised to negative 5, or the integral of 3x raised to negative 5. So we're going to separate the constant and find the derivative of this one, which is x raised to negative 5, and we have here 3 times x raised to negative 4 over negative 4 plus c. So that is the result after finding the derivative of the antiderivative of the function. So now let's evaluate the integral of this the integral of negative 3 over 4x raised to 4 from t to 1. So in finding or evaluating the integral of this one, is we're going to to find the difference after substituting the upper limit and the lower limit, because this is a definite integral. So first is we're going to substitute the upper limit, which is 1, to the function. So we have here 1 as the value of x. So we have here negative 3 over 4 multiplied to 1 raised to 4 minus uh, negative 3 over 4 multiplied to t raised to 4, because t is our lower limit, so we just substitute t here, and the result is equal to this one. So now we have here negative 3/4 plus 3 all over 4 multiplied to t raised to 4, and at this point we can now evaluate the limit of this one. We can now evaluate the limit of negative 3/4 plus 3 all over 4 t raised to 4 as t approaches to 0 to the right. So now let's just substitute 0 as the value of t. So we have here negative 3/4 plus 3 all over 4 multiplied to 0 raised to 4, which results to this one. And the limit is equal to infinity. And if the limit or the result after finding the or evaluating the definite integral is doesn't have an exact value, and the result is infinity, therefore the function is divergent. So for this example, we have here x multiplied to e raised to negative x squared dx, or the integral of x multiplied to e raised to negative x squared dx from negative infinity to positive infinity. So this is an improper integral. So in order to solve this problem, we're going to split the integral at 0, which takes on this form. And in order to solve this problem, we're going to find the integral of this one. So we're going to use u substitution. So let u equal to negative x squared, and du is equal to negative 2x dx. And we're going to divide both sides by 2, and we have here this one. And we're going to substitute the following values. And after doing that, we have here the result, which is equal to a negative 1/2 multiplied to e raised to negative x squared plus c. And now we're going to evaluate the definite integral from a to 0, and we're going to evaluate this one also from 0 to b. And in evaluating that, we're just going to substitute the upper limit and the lower limit. So first is we're going to substitute 0, and for this one is we're going to substitute a. That's why we have here negative 1/2 e raised to 0 plus 1/2 e raised to negative a squared. So for this one, we also have here the upper and lower limit b and 0. So we're just going to substitute b, and we have here negative 1/2 e raised to negative b as the value of x squared plus 1/2 e raised to 0. So now we can now evaluate the limit of this one and this one. So the limit of negative 1/2 plus 1/2 e raised to negative a squared as a approaches to negative infinity. So we're just going to substitute negative infinity as the value of a, and the result is negative 1/2. And on this one is we're going to evaluate the limit of negative 1/2 e raised to negative b squared plus 1/2. So we're just going to substitute positive infinity as the value of b, and the result is this one. So we're going to add, and they have unlike signs, so negative 1/2 plus 1/2 is equal to 0, and 0 is the result after evaluating the improper integral. Therefore, the function, the integral of x multiplied to e raised to negative x squared dx from negative infinity to positive infinity is convergent because it has an exact value of 0.